Hey everybody, Mr. Bell's here again. This is a Precalc A video for section 2-3 on polynomials. Overall big picture for this, polynomials are functions that can be cubic, quartic, quadratic, whatever it is. But we're going to put all the other parts in it. So like 3x to the fourth plus 2x squared minus 7x plus 8. We're going to look at end behavior, what happens to these functions as x's head towards positive or negative infinities. We're going to look at how they're built, zeros of the functions, extremas of the functions, doing a bunch of algebra stuff with them, and I'm going to show you some things on your calculators and why certain things called multiplicities exist and what that means in terms of the graphs. Okay, so those are all the general topics. Hoping this will be good for you guys. Please take your time. Again, pause videos anytime you need to. Stay on top of your Pearson homework. And again, as always, let me know if you guys have questions. Please don't just try and get frustrated all on your own. I'm here to help. Here we go. So we're going to start off with something pretty basic. You guys have seen this a lot. So a transformational one. So you guys know that if I had a, what we'll call a base function or parent function, y equals x cubed, that would look just like this, right? Cubic function kind of goes through the origin. It's got rotational symmetry there. And then you guys know that all of these things are transforming that. So just a reminder again, a plus 2 on the outside of the parentheses means that's a vertical shifts going up. A minus 3 on the inside of the parentheses, that is a horizontal translation, and it actually goes to the right. Remember, if it's in parentheses, it goes the opposite direction of what's in here. So this one's going to go 3 to the right. We know that this number out in front here, because it's not directly with the x, we call that a vertical transformation, and that vertical thing in this case, because the number is less than 1, would be a vertical shrink. Remember, if the number was bigger than 1, that would be considered a vertical stretch. And then that little negative right there is going to flip it. So in this case, this branch would go here and that branch would go there. So that negative out here is a reflection over a horizontal line, or in this case, if it was just this one, would be the x-axis. But remember, we've got that transformation, translation up and over that we already have going on. Okay, so let's go ahead and throw that into our calculators and see if everything I just said actually is true. So on y equals, clear that out. So we got negative, I'm going to do 0.25. You can do 1/4 if you want. I'm going to do it like that. Parentheses x minus 3, close parentheses, raised to the third power. Make sure you bring your cursor back down. I oftentimes forget to do that and then take everything in its one spot. And I'm going to go ahead and hit zoom 6. And you're like, ooh, where is it? Oh, it looks just like that. So let's go again here and put in y equals x cubed. That was our original one. X raised to the third, and see how these two things are related. So you can see this has been this inflection point right here has been moved 3 to the right and 2 up. That's why the inflection point's there. And what you can see that this one's kind of skinny, but this one's kind of wide. So that's where the change from the 1/4 comes in. You can see that now the stuff that's here is moved up, and the stuff that's up here is moved down. That's that reflection. That's that negative over that problem. So that's where all those transformations are coming from. You guys know, let me clear that out. If I look back at this original graph again, that if I wanted to know the y-intercept, that would be a key point. I could find that right up there. If I wanted to know the x-intercept, that would be a key point here. If I had some more stuff going on right in here, it could be that I have some extremas, a local extrema, a local min, and a local max. I don't know that that one actually happens on this. I might need to look a little bit closer with it, but I'm pretty sure that that there isn't anything going on there. Now, if I did this, y equals, I just added something on the back end of here, like say plus 2x. Then, we'll see, then it's pretty obvious that I can get polynomials that have local mins and local maxes on this stuff just by transforming that a little bit. Again, not saying that you just randomly do that to the equation, just showing you that those things can exist on those. Okay, good deal. So we're going to look next at this thing called end behavior. So something called limit notation. So what does that mean? When we have these polynomials, x to the third and x to the fourth and x to the fifth and x squared, whatever it is, what does the end behavior look like? So we're going to start off with odd degrees. Y equals x to the nth when n is an odd number. So like examples, y equals x to the first, y equals x cubed, y equals x to the fifth. You know that this is a line, this is a cubic, this is a fifth degree polynomial. And again, x to the fifth and x cubed aren't going to look much different, but if there's all these other stuff that goes with them, we can get them to do the stuff that they're showing right here. Now, if the leading coefficient, the number in front of the x's, are all positive, this is what will happen. And what that means is the right-hand part of the graph will head towards positive infinity, and the left-hand part of the graph will head towards negative infinity. Now, of course, if there's a negative in front of any of these x's, that of course would flip it, and it would change the end behavior. So let's take this one, for instance, y equals x cubed plus 2x squared minus 7x plus 4. I know that this stuff's going to do a lot of things to it, but I want to know what is the limit, LIM, of the function. We'll say, let me change notation just so you guys have that. So we'll call it f of x equals that. What's the limit of f of x as x approaches infinity? What does it equal? And then we'd also ask, what's the limit of f of x equal as x approaches negative infinity? And that's what we're talking about, notations for these limits. So what happens to this polynomial when x gets really, really big? Well, you can see that the x cubed term is going to have the most power, and it's going to outweigh a 2x squared and minus 7x and a 4, even if you throw all those together, when x gets really, really big. Now, if x is really small, then the 4, again, if x was like 0.001, then the 4 would have a lot more power. But we're only talking about x's when they approach infinities, okay? So on this one, what's the limit of this function as x approaches infinity? Well, it's going to grow up. It's going to get bigger and bigger in terms of its y. How about when it approaches negative infinity, when it goes to the left, like a negative 15 billion cubed is a huge negative number. 3 negatives still make a negative, right? So that would be negative infinity. That would be the limit for those ones. And again, it's not positive and negative because of just it is. That's what the graph actually does. Now, if I had let's put an a in here. If I had a number in front of that that happened to be negative, then these two graphs would invert, right? They would flip upside down in that case. Sorry if that was blurry for you. Just check my screen over there. Then, again, if this was f of x equals negative x cubed stuff, then the limit of the function as x approached infinity would actually go towards negative infinity, because then this polynomial looks like this, right? With a negative leading coefficient. So as the x gets bigger, it heads down. As the x gets smaller, it heads up. So that's what cubics do, and all odd ones go the same. All even ones, so if n is even, they go the same direction. So x squared goes up, negative x squared goes down, x to the fourth goes up, even if it's got little humpy stuff in the middle. Negative x to the fourth, end behavior, right, whatever that does in there, goes down. So even degrees, they go same directions. Odd degrees, they go opposite directions. Leading coefficients change whether or not they go up or down. And then, again, this is our notation. Just saying, what does the function head towards? Its end behavior when x's get really big or really small. Okay? So that's basic on that. Now, we've done a lot of factoring stuff, so there's going to be a whole nother thing on factoring, because when we have these polynomials, and that's what 2-3 is about, extended or advanced polynomial functions, we want to be able to know some of the things. And factoring allows us to tell the zeros of the function. So we could have a real easy factoring problem like this one, or what should be easy for a class like this. And you look for factors of 14, 1 and 14, 2 and 7, and they need to add together to get -5. I'm hoping that you say x minus 7 and x plus 2 work out, so let's try it. They have to multiply together to get -14, so -7 times 2 is -14. They have to add together to get -5, x minus 7, so -7 and positive 2. Adds together to get -5. We're doing great. Yay, smiley face. So that means that I could factor it into these two parts, which means that if I'm taking a look at my graph, it needs to touch the x-axis. 1, 2, 3, 4, 5, 6, 7. It crosses right there, and at -2. Is that good? Now, a couple other things we should know, and this is what building these functions means. This is a degree 2 polynomial, right? With a positive leading coefficient, which means the branches have to go like this. So if we were trying to sketch it, I know it's a parabola that goes like that. We also know that the line of symmetry has to be right in between those two things. So 7 and -2 is 5. So that means the line of symmetry is right there at 2.5. So I could plug 2.5 into this function and find out what that gives me, and that would tell me what my vertex is way down there. I also know my y-intercept is -14, so let me put a little breakage in there, and let's call that -14 right down there. So I'm building a lot of stuff in this polynomial because of the fact that I knew how to factor it and know symmetry, and I know properties of these things. Okay, so this one looks a little bit sketchier, a little bit scarier. This is a cubic function. But again, if I can use some factoring skills, I might be able to learn some stuff about this cubic function. Oh, let me time this out. Go ahead, put that into your calculator, check and see if all the things I did without the calc actually match up perfectly for it. You can even throw in and check the vertex to see that it is 2.5 and whatever that number is. Okay? So let's go now here, since you paused the video and you actually did the calculator stuff. So the first thing I'm going to do is, hey, can I pull a 2 out of all these? Well, I can pull a 2 out of this. I can pull a 2 out of this. Crap, I can't pull a 2 out of this. So am I done factoring like a dentist? Hopefully your answer is no, because look, there's an x in all of these things. So I know I can pull out an x, and I'm left with 2x squared minus 5x minus 12. I'm like, ooh, I have a leading coefficient of 2. Can I do that? And again, this is a pre-calc class. This is in the basic data class. This is where we should be able to do some of these things. So I know I got 2x and x. And factors of 12 are 1 and 12, and 2 and 6, and 3 and 4. I need the differences to be 5 with these things. Well, I have a difference of 11, a difference of 4, and a difference of 1. And you're like, crap, none of those things work. But wait, there's a 2 there. So that means one of these numbers gets doubled. One of these sets of numbers gets doubled. Then I want to look for a difference. Well, I double the 12, that's 24, and 1 and 24 differ by 23. That doesn't help me. If I double the 6, that's 12. 12 and 2 differ by 10. That doesn't help me. Remember, my key goal is a 5. If I double the 4, that's 8. 8 and 3 differ by 5. Awesome. So that means I need to have the 4 go here and the 3 go there. Again, you can check. 2 times 4 is 8. 3 times 1 is 3. 8 and 3 differ by 5. Therefore, the minus sign has to go with the 4, and the plus sign has to go with the 3. I now know that on this polynomial, right, watch my little sketch here, that I've found 3 different zeros. I know I have a 0 at 0. I know I have a 0 at 4. And I also have a 0 at negative 3 halves, right? Negative 3 over 2, negative 3 halves, or negative 1.5. I found my 3 zeros, and now what do I got? Oh yeah, I remember that this is a cubic with a positive leading coefficient, which means its end behavior has to go down from this branch and up from this branch. And I'm not going into specifics here, but generally speaking, it's going to have to do something like this, right? And I'm not saying how far down that goes or how far up that goes. That's a little bit further on in this course. But that my cubic function is going to have that general pattern going on from that thing, because I know my zeros and I know the end behavior, and that's kind of the stuff that I'm looking for. So let's do this together this time and make sure that we are in agreement. So I'm going to go on, y equals, clear. And then I got 2x to the third minus 5x squared, and then minus 12x. And zoom 6 it, cross my fingers, and I'm going to look carefully right there. You see, I think I have some zeros of that function. Looks like that one goes right around there between about 1.5 and the negative. That's good. Looks like it goes through the origin. It looks like it goes through 4. That's pretty good. Let me check my table setup. Started at 0. You can see I do have a 0 at 0 and 4. And now let's check. Oop, I can't check negative 1.5 in this window, but if I change this to go up by 0.5s, now you can see at negative 1.5 there is my third 0, and poof, all of that worked. When I go back to the graph again, you can see that yes, it did go up to that peak. Now, in order to see it down here, this branch did go way down there, but again, I was just kind of giving you a general idea. Okay? So, we're doing pretty good. We've done some factoring. We learned how some of these things look based on our ability to be able to factor. What happens if I give you something in factored form? That should be pretty easy, right? Unless things happen that are a little bit bigger. So we're going to talk now about what happens with multiplicities. What happens when I don't just have one x plus 3 here, but I have 3 x plus 3s here. Or if I have 2 of these 2x minus 7s here and only one of these things. So I'm going to give you a general sense right now of this, and I'm hoping this will help out before I do this. So here we go. Here's on my picture. I know that at negative 3, it touches, right? Because a negative 3 would give me a 0 in that, and 0 times anything drops out. Here, 7 halves are 3.5. I know that something happens there. And at positive 2, I know that something happens there. But if you'll see here, 3, 4, 5, 6, this whole polynomial is degree 6, which means that it needs to leave going from here, going up, and leave from here going up, because the leading coefficient is positive, right? Positive 2 and 1 and 1. 2 times 1 times 1 is 2. Okay, so I know these things have to be going up. Ooh, because, I mean, normally I would think it would just go like this, but this has to be going up, and this has to be going up. So why? What the heck's going on with this thing, and why does it look the way that it does? So first off, let's go ahead and get a picture here. Y equals clear. So parentheses x plus 3 parentheses raised to the third power, and parentheses 2x minus 7, right? Raised to the second power, and then parentheses x minus 2, close parentheses, zoom 6. And this is going to be, kind of messy for you. Because it's Really hard to tell. There's a 3, there's a, and the, let me double check, make sure that I typed that in correctly. 2x minus 7 squared. Oh, see. I should have something at 3.5. My graph, and you can see I don't have anything showing at 3.5, and that's concerning to me right now. So what did I do here? Minus 3 would get me a 0 there, right? 3.5 should get me a 0 there, but it's not showing up. And a positive 2 gets me a 0 there. So, is it not? Is it really not there? I'm going to do this because the pixel density on this thing sometimes is a little sketchy. So I think it happens at 3.5. So I'm going to go to my window. Watch this. I'm going to go from 3 to 4 on my X. And remember, there was literally nothing there before. Oh my gosh, look at that. It actually shows up now between 3 and 4. So again, watch, zoom 6. And I look at between 3 and 4, which is right here. Nothing exists on this screen, which really kind of sucks, right? Because when I do look at it really closely right in there, there actually was something there. In fact, it comes down, it touches, and it leaves. So here, my brain's actually smarter than the graphing calculator is. And maybe if I do this, I put this back to 0, and you can see some more stuff going on. Because you can see it does happen at 2, and then at 3.5, it comes back down again. Except when I spread this off, this thing's so straight up and down that you don't really even see it. It doesn't know how to turn pixels on. So I'm going to show you one more thing before I move off of this. Is I'm going to take my window and I'm going to take my Y max up here to 50, and I betcha it's going to show up here now. Did you see it? So there's the thing that's happening at 3.5. It's just so skinny because it's a degree 6 and it's growing so fast that it can't even light up the pixels that come down here to your thing. Okay? So now what's going on with this? So I'm going to tell you this. If it's just a degree 1, it'll go straight through the x-axis and it won't have any issues. If it's a degree 2, it will bounce on the axis at that point. And if it's a degree 3, it'll come through, but it'll curve. It won't go straight through. It'll have this little whoop whoop going through it. Degree 4, it will bounce again, but it'll be a flatter bounce, flatter than this one. This one will be a little bit steeper. Degree 5, let me just give you the other axis too. It's going to come in, it's going to be whoosh. It's going to be even flatter in that range. So let me kind of give you a little pictures of all these things again. So y equals x, we got zoom 6. You can see it'll go straight through, even if it's parentheses x minus 7. You can see it'll go straight through at 7. Just like that, yeah? But if I change that to a degree of 2, it will bounce at 7. If I change that to a degree of 3, oops, sorry, I did a raise to the power, so let me have that be 3 and that one deleted. You'll see that at 7, it does a little whoop whoop. If I do it a degree of 4, and on Desmos, this is so much better to be able to see this, and we do it in class on Desmos. Degree of 4, it bounces, but again, you can see it's a little flatter in that area. Okay, so that's kind of what happens with these multiplicities in terms of what's going on. So I know end results, because degree 3, 4, 5, and 6, I have to have something that goes up when it leaves on both of these situations. Because this at -3 is a cubic, it's going to come like that, right? It's going to have a little whoop whoop there, a little whoop whoop there. It's going to go down and touch someplace up there, right? Okay. At this one, at the 3.5, it's got to bounce, right? It's got to bounce. So that goes up there. And hopefully that makes sense. That means this has to do that. Now again, we said these things, the local max here and the local min here, they could be, because this is a degree 6 polynomial, right? They could be way up there and way down there. In fact, I'm going to try and find this one that's way down there. And I'll do a quick check on the y-intercept. The y-intercept will tell me that this goes down quite a bit. So the y-intercept is going to have a 3 cubed times a 2 times a, well, actually ignore the 2 for right now. 3 cubed times a 49, right, times a 2. So let's go home screen here. 3 cubed times 49 times 2. That means the y-intercept is down there at like negative 2,646. So when I go back to my original problem here, it's going to take me a while for you to see all this. It's going to go way down, trust me. Parentheses x plus 3. This is where it's good to be able to pause the video, because there's a lot of stuff we're doing right now. Parentheses 2x minus 7, close parentheses, squared, parentheses, x minus 2. Graph, right? So you can see that this goes way down there. Watch. My window, my y-min, I'm now going to go down to negative 3,000. Way down there. And you can see now that you can see the bottom portion of this. Let's make my y scales be 1,000 so I don't have all those tick marks there. And you can definitely see a local min. In fact, the minimum might even be close to what the y-intercept actually is. Okay? If I do a little trace and I go down here, you can see that that's right in that thing. Y-intercept's negative 2,646. So I'm going to do this. This is kind of zoom box 1. I'm going to do that here, here. Enter. I'm going to move it up. And I'm going to move it over. I'm just going to try and box in on this thing and see. Good deal. So now you can see the y-intercept isn't quite the lowest point. There's another point that's a little bit lower there. Again, just things to help manipulate stuff on the calculator. Okay. So that's if I had all these things factored, I can still find all that stuff and I can learn some things. Well, if it's not factored, if it's something like this, you still have to be able to use your knowledge to be able to get a window. So I would ask you to graph something big like this and throw it into your graphing calculator and then extend and look. So I know sometimes these videos are long, but there's a lot of material here. So I'm going to go x to the 5th plus 8x to the 4th, 8x raised to the 4th, minus x to the 3rd, minus 92x squared, minus 60x, and then plus 140. And if I hit zoom 6, you may or may not see some things that are going on. Okay, so first off, let's see if this makes sense. A degree 1 could touch the axis once, a degree 2 could touch the axis 2 times, a degree 3 could touch the axis 3 times. So if I have a degree 5, it could touch 5 times. And you can see 1, 2, 3, 4, 5. It really does touch 5 times. However, it's really hard to tell what's going on this. So I'm going to change some things. I'm going to make my x min negative 8 and my x max 5. I think that would show all those things. Delete. But my y min, I know it goes well down further, so I'm going to start off with 100 and 100 and see if I get anything else out of this. Oop! Do you see that you start to see some of these curves on it? So I need to go a little bit higher here, a little bit lower there. I also don't like that thick line there, so that's a y scale, right? So I'm going to make my y scale 250, and I'm going to go up to negative, or down to negative 300 and up to 300. 300. Just to try and get a little bit better picture, see if I can see everything now on this function. No, I can see it. Good deal. So hopefully you understand a little bit more about how to manipulate the calculator to be able to get to see big, scary equations and how we change our x's and our y's with that. Because again, if I did zoom 6 and I said, hey, what does this thing look like? You'd be like, oh, flipping no. Looks like a bunch of straight lines almost, right? In fact, it looks like these last two lines are perfectly straight. So I don't know if they're coming from up, down, or down, up, or which way they're coming. But I do know, because this is an x to the 5th, and it's a positive leading coefficient, that this one's really going up here, and going from down up, and this one's coming from down up that way. Okay, are you guys good? So, what else do I have here? Because that's a lot of stuff. There's nothing if only, right? So, unfortunately, there's probably about 10 more minutes here of stuff. And I'm going to try and go through quick. Here we go. So what if I tell you that a polynomial has zeros that are like this, and that f of 4 actually equals 36? Can you work backwards and find that polynomial? This is going to build into some much bigger things, so make sure our practice is good here. So if I said if a polynomial has zeros of -2, -√3, and √3, that means that x plus 2 has to be a factor, that x plus √3 has to be a factor, and that x minus √3 has to be a factor. And I also know that f of 4 must equal 36. Okay, so what I'm going to do is I'm going to try and build this polynomial back up. So if I multiply these two things together, hopefully you see that I get x squared. √3x and minus √3x are going to cancel. So √3 times -√3 is -3. So I know I have that times that. Is that good? I'm going to multiply these two things together, and I'm going to get x cubed. And then I'm going to get plus 2x squared minus 3x minus 6. So my polynomial is x cubed plus 2x squared minus 3x minus 6. So right now f of x equals that. So let me try it with 4. So I plug 4 into here. 4 cubed is 64. And 4 squared is 16. 16 times 2 is 32, plus 32. 4 times -3 is minus 12, and then a minus 6. 64 and 32 is 96. Minus 6 is 90. I got that to be 78. 78. I think that's right. Somehow I've got to have something that actually is out here in front, some multiplier m, that's going to do, when I plug that 4 in there, instead of getting 78, I need it to equal 36. So something times 78 actually equals 36. Let me double check my math before I mess you guys up here. So 64 plus 32, enter, minus 12, enter, minus 6, enter, 78. Yep. Okay, so what number? There has to be something that multiplies this entire thing to that 78 that actually equals 36. Well, I just divide by that. So 38, right? Oops, sorry. Excuse me. 36 divided by 78. 0.4615. Ooh, scary. So let's do this. Math, frac. Let's just reduce that fraction. And 6/13. So I know that I have to have a constant multiplier of 6/13 in front of this whole thing. So that number out there in front is 6/13. And you're like, ooh, that was kind of weird. Well, I actually am giving you a harder problem right now than what we would typically see, so that you can deal with some of the easier ones that are there. So watch. Clear onto this. So parentheses, x plus 2, close parentheses, parentheses, x plus root 3, close parentheses, parentheses, x minus root 3, close parentheses like that, and zoom 6. Dun, 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 dun. And supposedly this is what happens is that it goes through at positive root 3, at negative root 3, and at negative 2. So if I look really closely right here, because negative root 3 is like really close to that, right? That's negative 1.7 and negative 2. So two things are kind of happening here. So watch this. I'm going to trace and zoom in right about in that area, right about there, and zoom in just so you can see it, because I'm not so sure that you could see it before. But you see that? There's a couple pixels there. Let's zoom box right now, because again, so hard to tell. I'm going to go here, I'm going to go down, and I'm going to go over, and I'm going to zoom in on that area and hit enter. And now you can see that it actually does come up, right? And if I go trace, you can see that's 1.7, 1.72-ish, which home screen square root of 3 is right in that area. Are you good? So you can see, I know you couldn't tell before, but there are two solutions right there and one right there. However, if I do this, watch, f of 4, and I want to know the value at 4, this tells us the value of 4 is 78, right? But I'm saying the value of 4 needs to be 36. So watch what happens. This is kind of cool. Let me do this. I'm going to keep these the same. So I'm going to go vars, y vars, function, y1. And I'm going to multiply this by a random number, like 3. And I want you to see what's going on. So there's my original one. And here's my next one. See how it's steeper? Steeper. But look, it touches in the exact same places. A number out in front of these things, let me do another one here, just so you can see it, number out in front. So let's do 0.2. A number out in front, multiplying all of this stuff, doesn't change where it touches on the x-axis. It just changes if it's vertically stretched or shrinked. You can see that they both have the same zeros of the function. They just come in at different rates. So if I do this, insert what we said, 6/13, 6 divided by 13, and I regraph this. I'm going to get rid of this one now. If I regraph this, you'll see that it still has the exact same zeros, negative 2, negative root 3, and root 3, except now when I go to my table setup and I look at 4, 4 actually gives me an output of 36. Okay, that was where I was at then. Here we go. This one's going to be quick. This is how to use your calculator. This should be super good for you guys. How to use your calculator with data. So stat for clear all lists, enter stat, edit. I'm going to try and use cubic regression. So let's put in these 4 L1 values or x values. 0, enter, 2, enter, 4, enter, negative 3, enter, and 3, enter, 25, enter, 199, enter, negative 7.5, enter. And so hey, happy for all of you guys who've stuck around this long. So give me an email right now with the tagline or the statement, hey Mr. Bells, I watched your video all the way to the end, and strawberry lemonade. Yep, so type that into your thing. I watched your video all the way to the end and strawberry lemonade, and I'm going to get you some extra credit for this. So here we go. just finishing the rest of this stuff. So I'm going to go stat and calc and cubic regression. And I'm going to go ahead and store it in y1 vars function y1 calculate, and this is it. So there's my equation. So f of x equals 2.5x cubed plus 4x squared minus 7x plus 3. Now again, you can see I didn't just make up all of these numbers. I started with an answer and then I wrote the data down. So now that I have that equation right there, that's the first part. Can I find f of negative 2? Well, since I copied the equation into here from my thing, I can go ahead and go up to my table setup and go, let's start at negative 2. And I know that negative 2 equals 13. Good deal. So lots of stuff in here. Hopefully this was beneficial to you. And again, we're sitting at about 41 minutes right now, but that's typically what a normal class would be. So that's what we need for section 2-3. Awesome job. Good luck to you. Stay on top of this. Hoping these videos are helpful. Reminder again, yes, you're watching this. The students of mine in this pre-calc class, you're some of the best and the brightest kids in this school. Expect more from yourself every day. Don't get down on yourself if something that we do in this class is hard, and I tell you, it's going to get more difficult. Treat it as a benefit to you. I care enough about you to make sure that this isn't a cakewalk through here. I care because I don't want you to get off to college later and go, holy crap, this class is kicking my butt. And I never had any challenges coming into it beforehand. And if you are finding several days in a row in this class where you're like, I'm not getting challenged by anything, you see me. I can amp it up very easy for you. Got that, Alex? If you're listening, and this is 2021, we'll talk to you later. Stay happy, stay healthy, be a good person. Bye.